Welcome back to further continuation of the plastic analysis. So in the last lecture we had studied about the theorems of plastic analysis, the upper bound theorem and the lower bound theorem, whereas the upper bound theorem, it states that if we are able to guess some possible mechanisms of failure of a structure, then all of these shall be defining the upper bounds. That is, the actual collapse load will be equal to or less than the lowest of these. And then the lower bound theorem states that if we can find such mechanisms which are satisfying the conditions of equilibrium and yield, then such a mechanism shall be a lower bound. That is, the loads corresponding to this particular mechanism shall be on the lower side of the actual collapse load. Hence, if both the upper and the lower bound theorems are satisfied, then we are very sure that we have found the exact failure mechanism. Now let's continue further and let's define the analysis procedure, how we'll be applying these two theorems. So our first step will be that we'll formulate some possible collapse mechanisms, and here limited guesswork is involved in the case of indeterminate structures, but then we'll devise some guidelines based on the experience we have gained so far. For example, we have this information that if the structure is an indeterminate structure, then if the degree of indeterminacy is 2, we'll need 3 hinges to form, and there may be possible ways or scenarios in which the hinges can be formed. So that's the next matter, but at least we'll devise some kind of rules that will help us. Next, once we have done it, then according to the upper bound theorem, all these mechanisms, their collapse loads, they basically represent the upper bound. They are equal to or higher than the actual collapse load. So what we do is that we choose the lowest among these values, and that we say as the critical of the failure load, and in order to make sure that we have not missed out the actual and the true mechanism, we do now the equilibrium and the yield check. That is, we apply the lower bound theorem. So that ensures that if the lower bound theorem is satisfied, it ensures that the mechanism identified is basically the lower bound. So if both the upper bound and the lower bound theorems are satisfied, then we are very sure that we have identified the correct failure mechanism, and whatever is the load we are computing, that is the actual ultimate failure load of the structure. So let's apply this principle on a beam. So here we have a beam which is a sort of prop cantilever, and this is under a UDL. So for the method we are using the method of virtual work, so we don't need the actual values involved with the bending moment diagram. We just need to know the qualitative shape of the bending moment diagram. For example, here we don't need to compute the values of the bending moment at the key locations as per the elastic analysis. In the longhand method, we need to determine these values from analysis, so this step is not required here. The bending moment is hogging near the support and sagging away from the support. So let's say the maximum of the sagging moment occurs at B, and this is located at a distance x from the fixed support. So we have two possible hinges because the degree of static indeterminacy of the structure is 1. So if that occurs, then we'll have the plastic moment at A and also at B. So at both these locations we will have plastic moment. Now we assume that the structure is at the verge of collapse, and at this condition we apply small virtual displacement at B such that the two parts AB and BC, they undergo rigid body rotations. So something like this we are enforcing. So what happens is that both the plastic moments at A and B, they do virtual work as we apply the virtual displacements, which are very small. So what happens is that at A the rotation is theta, and at C the rotation is phi, and at B the rotation will be sum of these, that is theta plus phi. So now we can write the equation for the virtual work. We equate the external virtual work with the internal virtual work, and now to compute the external virtual work done by the distributed loads, the UDL, what we have to do, we have to take an infinitesimally small region and find out what is the work done when this particular region, it undergoes displacement in the downward direction, followed by integration over the entire length. Alternatively, what we can do, we can just find out the CG of part AB, and it moves down by a certain amount, and same strategy we can apply for part BC, and in this way we can write this equation. So here the left part situated on the portion of length x, so the total load is Wx, and it moves down by an amount delta by 2. So this movement delta by 2 is basically the displacement of the CG of AB. Similarly for BC, this also moves down by an amount delta by 2 with reference to the CG of BC. So we have the total loads Wx and WL minus x, and these are the external works which are added up, and then we have the internal works which are done at A and B. So at A we have MP theta, and at B we have MP theta plus phi. Now we can also substitute here the values of theta and phi in terms of delta and x, and by solving this equation we get an expression for W. Now what we find is that there are infinite mechanisms depending on the value of x. So which mechanism is the actual mechanism? So we find the lowest of these. So what we do, we take the first derivative with respect to x equal to 0, and this gives us the value of x equal to 0.586 L, and the corresponding ultimate load comes out to be 11.65 MP by L square. So this is the UDL, that's why we have MP by L square. In the previous examples we had MP by L because it was a concentrated load. Now according to the upper bound theorem, this load could be greater than or equal to the actual collapse load of the structure, and to ensure that we have identified the correct mechanism, we need to use the lower bound theorem and check for the yield and the equilibrium conditions. So let's do that. First we do equilibrium check. So how do we do equilibrium check? Typically what we do, we divide the structure into two parts and independently work out the reactions, and then we check for the overall equilibrium of the entire structure. So what we do, we have the two parts AB and BC. For part AB we find out the reaction RA, because now we have assumed that we have the moment MP at A and B, so we have drawn the free body diagram. So using this we can very easily find the value of RA, and similarly for BC, making use of again the free body diagram and the fact that the bending moment is MP at B. So just note the directions of the moments when we are drawing the free body diagrams. So the moments, they are basically internal moments, so the two are, so based on these free body diagrams we can find out the reactions RA and RC, which come out to be 0.586 WL and 0.414 WL respectively. So these have been independently worked out. So now we can check for the overall vertical equilibrium, and this comes out to be equal to WL. So that means the equilibrium check is satisfied. Next is the yield condition. So for yield condition, we know that the indeterminacy of the structure is 1. So what we assume that at A we have the moment MP and we keep the moment at B as unknown, and try to use the equilibrium of the parts to obtain the moment at B. So this has to be always less than or equal to MP. So what we have done is that based on these boundary conditions we obtain the reactions. So in this situation we have only assumed that at A the bending moment is MP. So based on this information we can find out the values of the reactions. So these reactions are now independently obtained. So we are not referring to the previous values but obtained using this configuration only. So once we have these reactions, we can then compute the bending moment at B, that is MB, using simple equilibrium of the part AB, and the answer comes out to be MP. So this means that the yield condition is satisfied. Alternatively, we can assume that the bending moment at B is equal to MP, and we can keep the bending moment at A as unknown, and we can compute by following this procedure. So it has to be less than or equal to MP. So both ways we can do yield check. Now we have already come to one observation that in an indeterminate structure the number of plastic hinges required to bring about the total collapse of the structure, that is equal to 1 plus the degree of indeterminacy. So this fact we can now utilize in solving the problems, and also we derive one more mathematical formulation for helping us. So if n is the total number of possible hinge locations, for example here there are 2 possible hinge locations, and if r is the degree of indeterminacy, then the possible independent mechanisms, their number is equal to n minus r. For example, here we are getting the number of possible mechanisms as 1. So this is the possible mechanism. So here there are 2 hinges, and these 2 hinges, it's easy to visualize that these 2 locations, one at the support and other just under the load, they are required to bring about the total transformation of the structure into a mechanism. So we have basically one independent mechanism for this case. So basically we can take help from this relation m equal to n minus r. M is the number of possible mechanisms, n is the number of possible hinge locations, and r is the degree of indeterminacy. However, please note that these values, they are suggestive only, and we need to keep our eyes open to look for something missing. So let's take an example. So we have this structure, again a prop cantilever under 2 point loads at 1/3 distance from the respective supports, and here is the qualitative bending moment diagram. So the bending moment at points B and C, we are not sure which will be larger, which will be smaller. So these are just tentatively drawn, because in this method we are not required to compute the actual values, but we just need to have an idea about the shape of the bending moment diagram. So now here we can apply our approach. So how to identify the possible hinge locations? So basically the points of discontinuity are the points of maximum bending moment diagrams, they are the possible hinge locations. So we have here 3 possible hinge locations where hinges can form, one at the support, one under the load P at point B, and the other under load P at point C. These are the possible hinge locations. So here n is 3, and because the degree of indeterminacy is 1, So this equation tells us that there are two possible mechanisms. Now how to identify those two possible mechanisms? That's the next step. So we can deliberate about the structure, and let's say we come out with these two possible mechanisms, that is plastic hinge forms at A and B, so that the structure fails in this pattern. And the other possibility is that the plastic hinges, they occur at C and B, and there is no plastic hinge formation at A, the support, so the structure undergoes collapse like this. So these look reasonable, and we try to find out the values of the ultimate load corresponding to these mechanisms just by equating the external and the internal virtual works. So we find out that in the first case the ultimate failure load is 5/3 of MP by L, and in the second case it's equal to 3 MP by L. So of course the lowest of the two, that qualifies as a possible failure mechanism, so we can always eliminate PU2 because it's higher value. So this one is a possible mechanism, but we can be very sure if it satisfies the equilibrium and the yield condition. So let's do that. So the upper bound theorem says that these two mechanisms, they are the upper bound, and now we are using the lower bound theorem, that is equilibrium and the yield check, to ascertain. So now we apply the ultimate loads as we have obtained from the previous step for P1, and we have the MP at these 2 points at A and B, and so now we consider the equilibrium. So we consider two parts B, C, D and AB, and we try to find out the reaction at D, and similarly we consider the part AB and we find out the reaction at A, and then we combine and we try to check the vertical equilibrium, and the vertical equilibrium is indeed satisfied. Now we come to the yield check. So for yield check, basically we know that this structure has an indeterminacy of 1. So at one particular point, let's say at B, we assume that the bending moment is equal to the plastic moment capacity MP, and we keep the bending moment at A and C as unknowns, and with this information we try to find out the bending moments at these 2 points B and C. So we begin with BCD, and if we make use of BCD, we can find out the reaction RD, and then from the overall vertical equilibrium of the entire structure we can find out RA. So you can do these calculations yourself, and once we have these 2 reactions, then we can find out the moment MA from the overall moment equilibrium of the entire structure. This comes out to be MP. So is it a good news? Yes, good news, but then we have to investigate further, because at A we definitely have the moment equal to MP, but then should we check at point C also? Yes, we should check at point C also, though it looks very obvious that the moment at C would be less than MP, but there is no harm in checking, because sometimes we get surprise in the plastic analysis. So once we do this, so we just make use of the equilibrium, and from the part A, B, C we can work out what's the internal bending moment at C, or alternately using part CD we can find out what is the bending moment, and to our surprise what we find is that the bending moment at C is coming out to be greater than MP. So this means that the yield condition is not satisfied. So that means this is not the true failure mechanism. But where is the failure mechanism? So let's again do a critical check by inspection. So basically this is the second mechanism, which we had found that this gives a higher load, but the first mechanism where there is basically the hinge formation at the support. So there are two possibilities. So we had explored only one possibility, that is 1A. We had missed out 1B. So basically the equation had given us the possible mechanisms as 2, but within this particular mechanism number 1 there are two possibilities. So this involves hinge formation at the support, and the other location of the hinge could be either B or C. We must check now this failure mechanism. So we have ruled out mechanism 2, we have ruled out mechanism 1A. So let's make check for 1B. So this is the mechanism, and we have the hinges at A and C, and if we use the virtual work method, we find out the value of the ultimate failure load as 4/3 MP/L. So this is a good news because this is lower than what we had found from the other mechanism, right? So it's lower than PU1. Let's now check for the equilibrium and the yield condition. So basically we have here A, B, C part, and then we have the CD part. So what we do yield check at A and we do yield check at B, and for this purpose we assume that the bending moment is MP at C. So this is the same strategy we had used for the previous case. So let's do the yield check. We are not doing the equilibrium check. Equilibrium check you can do yourself. So we apply here the loads and the moment we assume MP at C. All we have to do is now find out the bending moment at A and at B, so which we can now do very easily by using equilibrium of the whole structure or the parts. So we are only assuming that the bending moment is MP at C. So if we use the equilibrium of CD and then the overall vertical equilibrium, we can find out the reactions RD and RA based on this information. So these reactions have to be worked out now independently. We don't have to use the previous results. And then we find out the moment at A by overall moment equilibrium at A, and what we find that moment at A is equal to MP. And similarly we can work out the moment at point B, and this comes out to be 2/3 of MP. So here the yield criteria is satisfied. So that means this is the true mechanism. So please note that what we have used here, that we have kept MA as the unknown and MB as the unknown, and we have worked out these moments based on the assumption that we have MP reached at C. So this method we need to follow for the beams. Now we have two practice problems for you. Both structures have the degree of static interdependency equal to 1. Now for problem number 1, you can first solve by the first principle, that is how the hinges they are formed, by first carrying out the elastic analysis and finding out all the bending moments, and then deciding where the first hinge will be formed, find out the load corresponding to the first hinge. Then once the first hinge is formed, treat that point as a hinge and apply the incremental load and find out what additional load shall be required for the formation of the second hinge. So this way you can solve by the first principles, and after that you use the virtual work combined with the upper bound and the lower bound theorem. So both ways you can do, and you can compare the results, and also you can compare what internal structure realizations you get from the two methods. And question number 2 you can just solve by using the principle of virtual work and the upper bound and the lower bound theorems. So thank you very much. So after this we all shall assemble in the MS Team channel to have further discussion and also for your question answers.